Okay, good morning everybody. So, I am going to talk about the bird's flight today morning, and based on whenever you make artificial bird, we call it ornithopter, and design of an ornithopter. Some of the designs you can see already here, some of the pictures that we have built. So, briefly I will go through the activity, how it started, we did, because finally I want to show the motivation behind this successful design. Okay, so I have to acknowledge two of my PhD students who are working on this, Saurabh and Joydeep, and they started the work in their masters and continued in PhD, both of them. I also have to acknowledge for this work several organizations, that is National Program of Micro Air Vehicle, sponsored by Aeronautical Research and Development Board and DST, and the PIV system, for which I should thank DST FIST program. US Air Force for initially I started the work of insect flight with the support from US Air Force Office of Aerospace Research, and currently we are looking for an autonomous vehicle which is supported by IIT Kanpur, a large vehicle. So, I will be starting with this insect flight and then go on a little bit, but before that I will just give a brief overview, in the sense I know that there are a lot of young faculties also there from the engineering colleges, and I taught them, it's not teaching, I gave some lecture in the TechKeep thing with, and I had some interaction with them in the potential flow, and precisely that is why I would like to show them that how we can use potential flow even in this kind of complex situations. Okay, so the motivation of this work, if you see, the flying is in human mind, and it has been first documented probably by Leonardo da Vinci's sketch, and that is in 14th century, and then in 19th century Lilienthal really took it up with his glider, where he tried to model the wing similar to the bird's wing. And if you see that his work closely, there are a lot of interesting things that you can find it out, and in our motivation, this picture actually helped us to understand little bit what is happening on the birds. So, this is a storks flying, this is the downstroke and upstroke, and if you see the each cross section, these are like aerofoil, and they are varying from root to tip, their angle of attack is varying, you can see. So, this twisting of this wing is probably key, because upstroke and downstroke, they are different for successfully flying these birds. And as we were planning to build some smaller size of that, obviously, but some bird size thing. So, we looked into this, and we got the idea from this picture, you can say. So, if you look into the weight versus cruising speed of all vehicles, man-made or natural, then it will fall in this. And if you see it closely, the insects, birds and airplanes, they fall in this region. So, when we try to design, we try to keep ourselves in this range, because we think that that is some way naturally optimized. I will show one example of insects where you will see that nature's design is to some extent optimized through evolution or whatever need, and we never tried to build something which will fall in this region, because we may not succeed in that case. So, that was the first step towards design. Then if you see corresponding weight to length, then if we are trying to build something about 100 to 400 grams, we think of size of about 30 to 50 to 1 meter kind of thing. Okay. So, that is the range we try to keep it from this data. These data are available over the years from different studies. So, this velocity versus weight or mass has a good correlation which is velocity is proportional to m to the power 1 by 6 in natural flyers. These are for natural flyers. So, this gives you probably the speed limitation for the weight that you get, that what is the kind of speed you can achieve in this flapping wing mechanism. So, it is taken from the nature. So, I do not claim that it has been proved or something. It is. So, now complexity of the design. If you see, the wing is quite flexible, and you can see how they can maneuver, and it is really a complex thing that we can look into. If we see this video, these birds migrates thousands of kilometers with this motion, and if you see that this is the downstroke starts with a full stretch wing, and then there is a folding of the wing, and if you see there is the little twisting of the wing, or the camber is changed in the wing. If you see, nowadays we try to design everything compact, and in the nature you have a compact design. This ladybird, if you see the motion of this ladybird. So, the wing is made, wing is protected, and now it opens it up, pumps blood in the wing veins and create the spars for the wing and the leading edge, and once it is created, it can fly. So, this is a slow motion video, a lot of such interesting slow motion video you can get in this website. So, you can see that eventually it will fly. Yeah, it is just so, now you can see it is a very nice wing, which you can be high aspect ratio wing you can think of. So, these designs are extremely complex. So, if you have to build anything to in the flapping wing regime, you have to probably follow these things. So, those who are slightly new in this area, for them the motion is flapping motion, that is the flapping. Then you are folding the wing during the upstroke, because during the downstroke you get the upward force because of the reaction. During the upstroke you will get negative force, which will be the negate the lift force it generates. So, they fold the wing to reduce that. They have also many other mechanisms. Then the birds can change their flying axis, the body axis, and the axis on which they are flapping. This I will address at the end. The wings need not to flap in with the body axis as the hinge axis. The hinge axis can be different from the body axis, and that is specifically required for maneuvering of these birds. Then you have the twisting that I discussed. Then you have feathering. Feathering is, they can, while flying, the angle of attack of each section will also change over the cycle. So, that is the feathering. If you look into more into this complexity, it is the same bird, thrust night angle, and flying at 4 meter per second and 8 meter per second. So, when you try to design it, you will think that you will make a kinematic arrangement to flap it at a particular fashion, and you see that the tip velocity or tip motion is different at 4 meter per second and 8 meter per second. So, at 4 meter per second it is the low speed. So, to generate the sufficient lift, it creates an angle, incident angle, which is more, okay, so that it can get a more angle of attack in each section also. So, the complexity is manifold in this, not only flexibility, but also the kinematics. So, exactly designing any of such thing is very, very difficult. So, now before going to the design, let us look into some of these parameters that we use. Obviously, the wing velocity at the wing tip, that is the wing tip velocity, we talk about the tip of the span, and r is the span here. Phi is the total angle it is flapping. So, 2 phi is that, and Reynolds number you can define with respect to the tip velocity, or with respect to the forward velocity you can also define a Reynolds number. The parameter, unsteady parameter that is important here, like reduced frequency, is J, which is forward velocity divided by the tip velocity. So, this is an important parameter to take care of unsteady effect, and I will show why it is. lift and thrust you can define in terms of tip velocity or the forward velocity. Now, you see when the unsteady effects becomes important. So, the J, this is Stephen Ho's work in 2003. So, if you see the J is the advanced ratio, which is the ratio of forward velocity divided by tip velocity. If the J value is greater than about 1.5 or so, the quasi-steady limit work. Okay. So, the quasi-steady limit will be applicable more or less in this region, but in this region the unsteady effects are very, very important. This what is this unsteady effect? We will show that. But if you have this is with a span wise rigid, that means you will see most of them have a rigid leading edge bar, and the flexibility is in the chordwise direction. Here it is a span wise flexible thing. So, in this case you probably cannot operate in the unsteady region. The birds which use the span wise flexibility like bats, they probably will be operating in this quasi steady region. So, I will talk about little bit about what happens in this using some of this techniques. So, mostly experiment with little theory. So, flow visualization, image and force measurement. So, I will not go into this detail, but I will go into this particle image velocimetry in little details. So, the model you can study for PIV or in a wind tunnel cannot be very big. When you make a model of say half a meter, it is difficult. We do not have that kind of wind tunnel at very low speed that can operate, because these are operating at low speeds. So, about few meter per second. So, we do it in a smaller tunnel or smaller model. So, in the model, the insects model, when we did the PIV measurement, we use this model which has a quick return mechanism 1:3. Now, this quick return mechanism is used by butterfly very nicely. So, downstroke is a lift producing stroke, upstroke is negative lift producing stroke. So, they deform the wing so that you can get net positive lift and thrust throughout the cycle. But at the same time, upstroke they do it quickly, so that the negative lift producing time period is less. So, butterfly use it with a time ratio of 1.2 to 1.4, and we have used this 1.3 time ratio. So, first and then we looked into we took a monarch butterfly shape and we just scaled it up and down, and this size is said at 1x model, 1.5x, 1.75x model is just Xerox zooming of this. Okay. So, now this is how we fix this butterfly shape wing, and then we look into that what is the flow field at different locations. We can see the wing position also, exactly wing how it is deforming, and we also look at with respect to some other wing of similar size and similar area. So, the aspect ratio 1.5 is this wing, and then we reduce the chord and increase the aspect ratio, and we look into their characteristics, force characteristics. So, force measurement we do in a tunnel which has a 600 by 900 mm, and this is about 5 centimeters. So, this is at the most like 50 mm. So, we are far from this, and we position it in the tunnel, and then we measure the forces. Force transducer is placed, this is the force transducer, and we operate in the speed range of this, because the tunnels are usually not designed for low speed like this, but we had to characterize this low speed tunnel, and we found that if we take a PDF of 300 second sample, then we get a free stream turbulence of 0.2%. We do PIV with a stereoscopic arrangement, we do the PIV. We also look into the tip motion. There is a forward and backward motion like rowing in the wing. So, we have a model that can simulate that. Okay. So, if you look into the PIV data, so this is 1.75x model, and it is starting downstroke. Okay. So, you see that there is a leading edge vortex forming along this wing surface. So, wing surface you can see, and this is the plane in which we are measuring. So, there is also a trailing edge vortex forming, and this vortex which is present, which is created in the earlier cycle. So, this is like wing vortex interaction that is happening. As you go, you see this wing vortex interaction quite prominent, which is Dickinson group initially termed as wake capture, which you will see in the literature. This leading edge vortex grows, and these leading edge vortex are very important for this kind of small insects, because this leading edge vortex gives you a suction peak. So, that region, because of which you get a very high lift in this situation. And this vortex is attached, you can see more or less throughout the downstroke. Then when it moves into the upstroke, so you can see that it starts moving into the upstroke, then you see an opposite circulation vortex will be forming, and these two vortices can interact and eject like a slug of fluid. Now, this ejection is we have observed in this butterfly shape thing, very nice, and we have also seen this in a larger model. I am not going into the entire details of this vortex interaction in this talk, because this talk we are more concerned with the design of an ornithopter. So, this ejection is one of the mechanism which they quickly use to maneuver. So, if they have to, so this ejection is associated with the force direction in this, so they can generate a left hand thrust in this. And we have seen at different parameters that can be ejection can be horizontal or ejection can be at any angle. So, they depending on the parameters, and they can control that. So, but this we have not, one has to really see in the natural butterfly, real butterfly, whether it is happening or not, doing some flow visualization, but that has to be done, those experiments. So, this is a different aerofoil model with a flexibility, and again you can see that during the stroke reversal there is a strong ejection here. So, these two vortices they eject like that. These ejections are usually happening at different cycles, like different frequency, it is happening at different time, and usually they are in the same time in the when you are non-dimensionalizing with respect to the total period of this cycle. During ejection, you see the very high thrust generation in this case. Okay. So, this we have seen both from load cell measurement and a control volume analysis from the PIV data, assuming the pressure is not important, because we do not have. The PIV, one of the advantages, you can get the other quantities like circulation and found out how this vortices are growing and decaying, which is very important to understand this kind of flow. So, this is the thrust data, and this data both you can see that during ejection period we get a very high thrust load. So, if this is the force in a complete cycle, and you see that different aspect ratio wing and the butterfly wing, and from this it is, although not very clear, the butterfly wing is slightly better, which we will show here. So, if you see the CL max and thrust max, so butterfly wing is this one, and if you see all others, this is the classical J versus CL curve you will find in most of the literature. And you see the shape is, butterfly shape is probably naturally optimized shape, where you are getting very high lift coefficient and thrust coefficient here. So, now I will just show quickly the effect of lead lag. So, if you see the lead lag, that is the forward and backward motion. So, if we take this signal from a transducer, force transducer, and if you take FFT, you will see that a lot of other vortex effects are there. So, that is the set vortexes we saw in the PIV images. So, these are related to flow. Flapping frequency is somewhere here, and that you will see for different. So, now what we do when we obtain the force data, we filter this high frequency part, and then we get this filtered data as the force data, and you will see that for other case also. But when you use this lead lag motion, this rowing motion, then you see the raw data itself does not contain all this high frequency this thing. And if you see a PIV image corresponding, you will see a very clean flow, clean leading edge and trailing edge vortices when you incorporate this lead lag motion in the flow. So, all these motions are, it's the message is that all the motions are important when we are talking about this flow, because PIV we could do only with the small one. So, I just showed some of the PIV result with the insects model. Now, you go to the birds model. Now, In the birds model, when we try to design, we have to get some design criteria, and I think this talk mostly I will be focusing on that. So, if you take a rigid wing, this is some of this earlier work, if you see the rigid wing when it is moving, then you will see this angle changes, feathering angle changes or twisting, you will see in this fashion. What you need is a flexible wing where the deformation will be more like what you see in the bird's wing. And that is why if you are able to deform the or copy this, mimic the bird's wing motion to some extent, understanding the predominant effects, then you can probably design. Now, we did that, and before going into the design, I will show some of this thing. So, how the flexibility is important, that to show while that above video is playing, I will show this. So, you see that wing is here, how it is deformed during the upstroke. So, you can see that the deformation of the wing is very, very important. So, if you see precisely here the wing shape, and here the way it is deformed is quite different. This is the same model which is flying, and in the near our hostel, this football ground, and these crows, they came chasing it. Okay. This model is a 1 meter wingspan model, and this model is a half a meter wingspan model. This is our first model we flew, and some of the tests that has been done is for a smaller model. So, this is the student who has a very good hand of building this. So, he has done this. Okay, this is RC controlled. So, he has a very good hand of flying also, making and flying. So, okay, wing is flexible plastic sheets, okay, of different thickness. So, it is to bring the flexibility, what kind of thickness we need, that is what we use. So, wing is that. So, this is the same model. I am showing this just because this we flew in this cricket ground or the stadium opposite to this. But when we change this color from red to blue, this is for biologists to see, the crows were not chasing it, but what chases them is the similar size bird. So, you will see some eagle will be visiting. I will show that later on of that experience. This is a different kind of flapper which can hover. Okay. So, there is a Delft group who are also working on this kind of flapping, and based on they have done a lot of experiments on this, and based on that I can stop this probably. So, based on that we have designed. So, I am not going to talk about this design here. So, you can see it can hover at a particular point. So, this is that student, and this is Dr. Abhishek, who is now part of this team to make it autonomous. Okay. So, now if we go into a little bit of aerodynamics, so we have to have a kind of twist distribution theta I in the spanwise direction. So, before making it, we thought how to estimate the force that we required, because see often when you start making such thing, the first thing that you will encounter, the motor you get, the total weight of your model, the size you make, and it will not able to fly, the it will not able to fly. So, you have to get some estimate of what will be your model size, and then what will be the lift it will generate. So, this is probably the very elementary level theory which we have upgraded now, but it is I am not showing it here. So, if you take any section from the root, and if it will be like a aerofoil shape, and you will see that it can have an angle that I showed in the thrust night angle, that angle with respect to the hinge axis, and this will be some angle of attack, because there is this omega y is the flapping component of the velocity. So, there will be a relative velocity. So, with respect to that you will get a force, which with respect to this you will get a force using the two-dimensional theory, which you can decompose. The drag is a estimation, just taking some drag coefficient, and from this lift and drag you will can decompose it into a vertical component of force and horizontal component of force. So, this is the lift you will get, and this is the thrust you will get in this configuration during the downstroke from one of this. During the downstroke, entire wing is having similar kind of configuration. So, all parts of the wing will be producing positive lift and positive thrust. Okay. This is the alpha s angle that I am talking about. Now, okay, this is just quickly for this calculations. We use lifting line theory, which is valid for steady flow, two-dimensional flow. So, the assumption is steady two-dimensional flow, and we are applying it for unsteady flow. So, it is, that's why I am saying the theory is very elementary. We are not taking the unsteady effect, we are not taking any three-dimensionality effect, we are not considering even the wing position, anhedral and dihedral position. We are only considering that wing in a level flight position and using this theory as it deforms. So, just to get an order of magnitude of the forces that it generates. So, here this is like for the people whom I was interacting with discussing with the potential flow theory. Here we have the wing is represented by vortices in the lifting line theory, and this gamma is the vortex circulation. Okay. And when we satisfy this no slip boundary condition and all, you will get this equation, and you can solve this and get the lift forces by getting the gamma, obtaining the which gamma will satisfy the which gamma distribution will satisfy the boundary condition of the aerofoil. So, this can be applied for a thin aerofoil, and that is how these calculations I am not showing here, but that is how we do it, the potential flow, how we apply in a problem as we discuss the potential flow in that discussion. Now, if you see during the upstroke, the same when it is in the upstroke condition, this omega is in this direction. Now, what you will get is a positive lift, but the negative thrust. So, you cannot fly even after deforming if you just deform in the same way, because you will get a negative thrust during the upstroke. So, you have to get positive thrust and positive lift, whether it is upstroke and downstroke. So, this configuration will give you positive lift, but negative thrust. But if we just reverse this camber, this is, let us say this is the camber line, this is thin aerofoil, then what you will get is a negative lift, but positive thrust. So, we thought that maybe they are doing this twist distribution in such a way that some part of the wing is in this configuration and some part of the wing in this configuration. So, the net effect is that integrated effect is you have a positive lift and thrust during the upstroke also. Otherwise, downstroke will produce lift and thrust, and upstroke it will go down. So, or it will not be able to fly. So, this is what we implemented, and this is the only thing that probably had made this model successfully flying. Otherwise, we could not have probably fly this. Now, what we do for after this from this calculation, suppose this part of the wing we have a negative camber, then some part we will have negative lift, some part will negative thrust, some part will have positive thrust, and this integrated effect we should get a net lift. If we change this amount of the length of the span-wise length over which it will have a negative camber, we can find out the net force how much it will be. So, now when we make a model, so suppose we are making a model of the order of some 25 gram, and if we have to do that, then we have to generate the force, the lift force of the order of 20 gram or so. So, we have to generate a lift force of that gram. So, we saw that at 6 meter per second at 8 hertz in this small model, we could get that thing. So, the first model that we built, that 300 wingspan, 500 wingspan, we use this because that is about 23 grams of model, and we could thought that okay, maybe this is this estimation we will use. So, you can do the power estimation and everything. So, this is how the wing is designed. Now, how do you gauge that reverse camber at some part and how do you get forward cambered at some part in the downstroke. So, if you see you will see that some flapping wing models, flying models are available in the market, and so if you see they have a leading edge spar, and usually they will connect from somewhere in the mid chord or to third position to somewhere one more spar here, and the flexibility they use only this part. So, they fly, but they do not fly so efficiently. What we did, we had just a leading edge spar, and we used this stiffeners in such a way that we get the deformation during the upstroke the way we want, that is the reverse camber. So, we build this model and we put it in a wind tunnel, and we have put it at that speed, and we use a 1000 frames per second high speed camera to look into that wing motion. So, if you see, this is the upstroke, and this part of the wing has a forward positive camber, and this part of the wing has a negative camber, reverse camber. So, we could successfully do that in this model, and during the downstroke you see that air wing has a positive camber. So, once we could build it, then once we confirm this, then we could build it, and it flew in the first this thing, the model we showed that this is the model. So, if you say that why did this theory work? So, then we went and put this model in the wind tunnel again with the load cell here, and simultaneously we looked at motion, wing motion with a high speed camera and measured the forces. And I am not, so the force cycle, you will see the time variation of the force will be similar like this. But if you see the net force effect, so at different speed, wind tunnel speed, the force, that vertical force and thrust that we got, we can see the thrust is quite nicely matched, lift is matched up to some discrepancy, because the theory is very. So, now one can say that can we not improve the theory? Yes, there is already existing improved theory. If you use the Theodorsson's model, then Theodorsson's model takes care of the unsteady effect. So, you can take care of that, and you can take the unsteady effect in that fashion. There is also a model by Phillips where this twist distribution is also used in 1981 JFM1 paper is there. So, those things one can use to see this how it is working. So, now we design the wing, we look into a CAD model, and we do the wing kinematics and fabricated the prototype. We flew it and find the flying performance for different models. And this is the smallest model. We had 25 centimeter wingspan, about 30 gram of this weight, flapping frequency of about 8.4 Hz, it flies as we should. The endurance of this with the battery that we had is about 10-12 minutes, because it cannot carry more than that. This model which we built, its weight is about 230 gram, flapping frequency. So, in nature, if you see the smaller the insects or birds, the flapping frequency is higher. So, flapping frequency you can fly it at a lower flapping frequency, and that is why probably the quasi-steady theory work more better there. And also we have seen the larger model is flying better, because the theory is 2-dimensional theory, and larger model has a better 2-dimensional approximation is probably working better there. So, this model we had the endurance in 25 to 30 minutes, and squeeze speed is of also 6 meter per second. Power consumption was about 12 watt. Now, this model and this model, the difference is just when you build something. This model is the first model we built for the larger one with the balsa wood and all these things, and the frame was also balsa wood frame. And as a result, what happened that there were a lot of friction. The gears which are mounted on it had lot of misalignment, was not that great, and all these things, and we got about 25 to 30 minutes. This to this exactly same as far as wing length and wing shape, everything is concerned. Only thing is this fuselage, it is covered with foam, but we had two this carbon fiber plates we had, on which we have mounted all the gears, everything arrangement. and this leading edge part is a carbon fiber rod. This is also carbon fiber, and these there is no balsa here. These two stiffeners, they need to be flexible and they need to be lightweight also. So balsa was not doing the best job. So what we did, balsa wood, you will be familiar with those who are doing it aero modeling. So what we did is we took the bamboo skins. So bamboo skin, and you can take the small part of the bamboo skin and make it very thin. So skin part of the bamboo thin is polished and thin also. You can make it very thin and stiff also, but it is also flexible. It does not break so easily. So these stiffeners we used. In fact, initially we used this also bamboo stick, and then we changed it to carbon fiber. But these things we realized that carbon fiber also cannot be so flexible, so it will break. So we through this trial finally we found out that bamboo sticks works better. So in this model, the difference between this and this is that you have a very nice fitted gear. In the losses in the gear is very less and all. So the power consumption went down to 10 watt, and the endurance, that is the flight time, went up with the same battery to about 30-35 minutes. So this can non-stop fly for about 30-35 minutes. So that these things. Now let me talk about quickly that little bit of the maneuverability, because previous part what I presented, many of the institute people have already probably heard that. So, so this part is recently we did that, how we can incorporate the maneuverability in this thing. So this we did in NAL, has a now National Laboratory has a MAB tunnel. So in that tunnel, the free stream velocity, based on free stream velocity, this Reynolds number, and frequency we've had it, so rotation and Reynolds number changed. And we did some experiments to see how we can incorporate maneuverability. But before experiment, you have to make a model which is slightly different. So if you see, this is the hinge axis, these two wings are flapping. So they flap. When they flap almost the same this thing, and this stroke plane is parallel to each other. Okay. So this actual stroke plane has some angle with the hinge axis, and then it is parallel to each other. If you, that means we are symmetrically flapping. Now if you can change this in a different way and this as a different way, then you have some independent control of this both. We also did a tail which has this tail could pitch up and down, and also it has the twisting. So this tail angle is theta. So now with this model, we did some experiment force measurement in the NAL tunnel, and if you see, so now these are the lift coefficient, thrust coefficient, and this is the side force. This was a 6-component balance where you can measure all 3 component of forces and moments. So this is the pitching moment, Cm is the pitching moment, Cn is the yawing moment, and Cl is the rolling moment. So theta r and theta L is, these are the this different stroke plane angle. Okay. So now when we change the theta r, theta L is 0, this is what your reference data you get. Then we have employ this tail to reduce this Cn coefficient, that is the Young moment. Sorry, Cn coefficient. So this is 0 degree, and then tail has an angle of 17.3 degree. 0 degree it would have been somewhere here, 17.3 it is somewhere here. So now when we have the stroke plane, both theta r and theta L is symmetric, 3.4 degree. This is what you observe, and when we change it to asymmetrically, you can see that these values, if you change this negative to this, moment coefficient changes quite a bit. So how do you use this? So these are used, these control forces are used to maneuver, and we thought, can we really do that maneuvering in these things? In fact, the idea was first built and then we saw it is working, then we did some test, and now if you see this flying, so this is like normal flapping flying, and now you can see that it can maneuver some part of the image is going out. Yeah, that is the point when it can maneuver. So, you can see the birds will come like this, snatch something and go up. So, this kind of maneuvering you can do with this. This is the no. It is capability of the flyer. So, you have to, but you have to have the model has the capability. Without that, you cannot do it. Obviously, if you do not have this stroke plane, differential stroke plane change, if you are not able to do, you cannot do this. With the other model, we cannot do that. Okay. Then we also looked at, because this is often a question, that how is this small flyers will work when there is a gusty situation. And this being a MAB tunnel, it has some arrangement to in this region to create some unsteadiness in the free stream. And this is what the unsteadiness you get. There are some veins which has some aerofoils, rotating aerofoils, which can divert the flow, some part of the flow in the downstream, and can create a unsteadiness in the free stream velocity here. So, depending on that RPM of those veins, you get different. This is 10 RPM and this is at the higher RPM, you get this kind of free stream unsteadiness. This tunnel has a velocity range of 0 to 45 meter per second with turbulence level lower, about 0.1% in 10 meter per second, up to 10 meter per second. This tunnel is designed to operate at low speed, so it is a good tunnel. And it also has an open jet section, so there is no wall here, so wall interference is not there when flapping. So, so we can see these are the force, but if you see this vertical force with respect to the no gust. So, if you see that this vertical force, it decreases slightly, the lift decreases slightly, thrust decreases quite a bit. So, that is why it is in the gusty condition, it is difficult to fly these things, but so you have to do this kind of test and design your model accordingly, and you can find out for what kind of gust condition this model can fly. Okay. So, this is what experimentally one can do, and that is what we are trying next to build something. So, at the end I will show one video. I do not know whether it will be visible or not. As I said, these birds are usually attacked by the similar size birds. So, we flew this in IIT Bombay campus once, and this is IIT Bombay campus. The picture here and there has lot of difference. So, the problem is I do not know whether you will be able to see. So, IIT Bombay campus, in front of mechanical department, we flew it. There is a lake there, and lot of this is our model, and lot of these natural kites are flying there, and you can see that it is trying to attack it, and in fact, it attacked it several times. And what is the surprising behavior we saw, that while one was attacking, there were about hundreds of others were flying above. So, this is just to show you that it will be attacked by similar size birds, unless we saw that if it was a red colored this thing. So, thank you. So, this is
so, what were those peaks?
In
you have not shown any light on that.
FFT.
FFT you have shown in the beginning. Yeah. So,
yeah. So, if you see, this is
first few peaks.
Yeah, first few peaks related to the vortices that you see. So, vortices are present over the wing. So, you will see those related to this vortice. This is the flapping frequency you see. Okay. These are some of these stray vortices that you see in the flow field. Like if you see the flow field, it is not very clean flow. You see lot of vortices are present in the flow field, and as I showed, they interact with the wing. While it is going down, they interact with the wing. So, in one cycle, the vortices that are generated, when it goes up by the next cycle, some of them are sucked in, like like I showed in one picture. Yeah, you can see some of these vortices are active. So, because of this presence of these so many vortices, you see lot of spikes. Okay, other than the some part of the vortex will be shading also. Okay, so we did not look into that details, because the PIV that we could do here is we cannot look into that detail unless we do some phase average measurement and all this, how much vortex has shade and all these things. We try to capture this leading edge, trailing edge vortex circulations and all, but in the process we saw some of these interactions and all. So, most of this those can be related probably with that.
Some systematic thing is happening there. That is why you see
So
nice frequency
you see this, but when we we filtered this to look the predominantly what we are getting the forces, but when you had this lead lag motion, most of these disturbances are gone. You can see that flow was much cleaner. So that is what we observed.
Thank you.
That graph that was there in the beginning regarding energy and weight.
Mass and weight?
Huh.
Yeah.
So if we are to make an ornithopter the size of like suppose this stage, then how much energy consumption would it be?
See, that is some guideline. It is, you are talking about these graphs. This is mass versus velocity. And this is
energy consumption.
Weight versus wing length. There is no energy consumption. This is cruise speed versus weight. Okay. So this gives you the size restriction. Okay. So energy, the power estimation you can do once you build once you design a model, let's say thing, you can use that theory and you can try to get a power estimation.
So if a similar size ornithopter and a helicopter was there, which one would use more energy?
It's very obvious. Helicopter has a rotating this thing, blades, and the rotating blade, the power consumption of the rotating blades are much higher compared to this thing. So this way, this can see, if you see today with the 4 blades, this quadcopter drone, which is you will see all around today in use, because it is very stable. You can hover it at some point. So we saw even in the crowd management, when there are a lot of crowd gathering, people fly there to see and all this thing. So those flies for 15 minutes. Okay, and every 15 minutes you have to change the battery or send a second one. Whereas this these are much lighter weight. This is only 260 gram weight, so it can fly 30-40 minutes. So I can tell you, we have made a 1.8 meter big one, and which can take much more weight will be much more for the battery, and which can fly for much longer, and we have seen that it flies very well. Yeah. Actually, that's what I said, that these vortices which are forming on the edge of the leading edge and the other part of the wing, because these are done with 0 advance ratio, that means there is no forward velocity. So some of these vortices will shed also. Okay, and so you can find out, and also during this reverse flow, this vortex and opposite vortex will form. Their interaction depends, which I showed one ejection phenomena, but that vortex-vortex interaction will depend on their strength. So it will depend on parameter. So
double frequency, no? So it should be just bifurcation rather than this high frequency, no?
I don't think they are just double frequency.
Yeah, roughly, but I think they're all high harmonics. 2F, 3F, 4F.
So if you see this, so this could be, but I don't think these are higher harmonics. First 4 or 5 you can explain actually, because this is over the cycle when you take, this you can explain that from the vortices how it is happening. Yeah.
What is the motor you are using?
Model?
Motor.
Motor. Okay, nowadays you get varieties of motors. So, you go to any hobby website, you will get different motors with different power, different torque, different these things, micro motors. So, you can you have to choose according to your requirement. So, that is, so Hobby King is one of the place where we purchase some of these things, but there are many other places.
So my question is related to the previous question or a couple of questions ago. I was wondering if you made a comparison between, so you showed power requirements for your various models, and I was wondering if you could comment on what similar sized birds or insects, I guess birds, consume. So there is data for the energy cost of birds flying at various speeds of various sizes. I was wondering if there's a comparison.
I have no idea. I don't have the answer at this point. One has to look into the available data, and it may be possible to find out the power requirement. But those birds, if you see the migratory birds, they weighs only about some 1-2 kgs, and they can fly for thousands of kilometers. So, any other question?
So if there are no more questions, we thank the speaker.